calculus students. Here's the second half of 1.1. Finding the domain of functions, and we're going to do some stuff later on with difference quotients. The domain of function are those values that can be put into it and still yield a real number. So when we look at something like f of x equals the square root of x minus 3, we can see that we can't just put any number in. F of negative 1 would be the square root of negative 1 minus 3, which is the square root of negative 4, which is 2i. That's not real. So negative 1 is not in the domain. Basically, in this case, the domain is going to be those values of x that make the radicand x minus 3 greater than or equal to 0. So x is greater than or equal to 3 is our domain for this function. And as we're going to see later on, when we graph this, it's going to go to 3, 0 and only have points to the right of 3, 0. Another way to think of domain is what values of x, what are all the values of x taken on by all the points of the function? So I like to think of it as snowfall. If we think of all the points on the function as dropping down here, like snow, from the function going straight down, and that part of the x-axis that gets covered up is the domain. And there's our domain again, colon, x greater than or equal to 3. So another way to think about functions, domain. Now, another restriction on functions is if you're possibly dividing by 0, because you can't divide by 0. So if we look at this function, fx equals 1 over x minus 2, x minus 2 cannot equal 0, so x cannot equal 2. So the domain on this function is x cannot equal 2. And as we look at the picture, we'll study how to graph these later on. 2 is going to be a vertical asymptote. Horizontal asymptote at 0. 0 goes to negative a half. And we get something that looks like this. It's hyperbola, the big horizontal asymptote here and vertical asymptote here. Now when we look at the snowfall effect, you have to think of all these points coming down and also all these points bubbling up, like bubbles when your paddle steers the muck in a pond. They come bubbling up like this. So you'll end up covering the whole x-axis except 0. So that's why the domain on this is everything but 2. So let's review that. Domain restrictions. They come from two basic ideas. The first one, the radicand must be greater than or equal to 0. And this is for even radicals. Like square root, 4th root, 6th root, and so forth. And the other domain restriction is that the denominator cannot equal 0, because that would create division by 0. And we saw those two in the last problem we did. Okay, we'll practice more of those in class, but that's the general idea of what to look for when you're restricting the domain. To figure out the range, you really have to get a good idea of the graph, and we're going to be working throughout this chapter on doing graphs. So, well, let's try one more. Find the domain of... Okay, here we go. Find the domain of the square root of x minus 1 over x minus 2. Now, this involves both ideas. First, we want to use the idea that the radicand, the thing under the radical, has to be greater than or equal to 0. So x minus 1 over x minus 2 has to be greater than or equal to 0. And basically, we can multiply both sides by x minus 2, but then we don't know if that's going to change the direction of the arrow there. So let's do our simple test chart here of what goes on with this function at 1 and 2. And if you try some points, you can see that something like 3 is going to make both positive, so 3 works. Tested 3 and it works. 1 will make it equal to 0, so I like that. 2 will make it undefined, though, so I don't like that. So we tested 3, yes. let's test 0. Test x equals 0. We get negative 1 over negative 2. That's a half. That's greater than or equal to 0. So yes, for x equals 0. So that means we shade in 0 and anything to the right over here. And finally, we have test stuff in between. Test x equals 1.5. X equals 1.5. So that ends up being 0.5 over negative 0.5. And that's negative 1. No, that's not greater than 0. So that's it. That's our domain restriction. The other thing to watch out for is, does x equals 2? X equals 2 makes division by 0, so we don't like that up there either. So that's why we've got that for our domain restriction, and we come up with our domain is x less than or equal to 1 or x strictly greater than 2 for the domain restriction. Now, the difference quotient. The difference quotient is a fancy way of saying slope. Slope is a difference quotient. Remember the formula? y2 minus y1 over x2 minus x1. That's a difference quotient. That's a difference put into a quotient form, this big division. Now, we're going to use this form a lot for the dq. The difference quotient equals f of x plus h minus f of x all over h. Or you can say f of x plus delta x minus f of x all over delta x, where delta x is the sort of change in x. So you're going to see in many forms. It looks different than over here, but basically we're calling this delta x the change in x's. And this difference in the f of x's, that's the change in y's. Let me show you on a diagram how that works. Here's our x and f of x, where this is the x-coordinate, and this is the x-coordinate with h added onto it, so that this gap between the 2 points is h. And then this gap between the 2 y's, the y-coordinate of this point is f of x, the y-coordinate between this point is f of x plus h. So when we look at difference quotient as the slope of the secant line, remember from geometry, is where it crosses the function twice. So it's f of x plus h minus f of x, that's the change in y's, over the change in x's, x plus h minus x. And you can see that the x and minus x cancel out, and so you just get f of x plus h minus f of x all over h. And we'll try an example of crunching through some of the algebra on it. Before that, I want you to give you a visual idea of where this is going in terms of functions. So I'm going to temporarily call up GeoGebra. And you can see here that I've got this point B on the function that I'm going to grab. And as I do that, as I grab this point, it changes the slope of the secant line. See, there's a bunch of slopes of secant lines. And what we're going to try and do, right now this is demonstrating difference quotients for 2 different points on there. I'm keeping the left point A fixed while I'm moving this B point along. And eventually we want to be able to have these 2 points become 1. But watch what happens. I get undefined when I put them together, because you'll have 0 divided by 0. So we have to carefully study the limit process as we bring these 2 points closer and closer. See how the slope is getting steeper and steeper and steeper, but it's not going off to infinity. It looks like it's getting closer and closer and closer and closer to what? We'll talk about that in class. What do you think this is getting closer to? Because when I put it right over each other, it goes to undefined. So we'll work on this one in class. Okay, back to our other board. Let's actually try doing a difference quotient now. The difference quotient. Find the difference quotient of f of x equals x squared plus 2x plus 3. So first let's analyze what these different things are. What is f of x plus h going to be? Got to be careful there. That's going to be x plus h quantity squared plus 2 times x plus h plus 3. See, I put x plus h in wherever I saw an x. So now to do the dq, the difference quotient, that's going to be equal to f of x plus h minus f of x all over h. And each time, you have to be given how f is defined, the function. Don't think you have to memorize that f of x always equals this. It could be anything. So, let's substitute in these values then. F of x plus h, like we saw up here in red, was x plus h squared plus 2 times x plus h plus 3. Now we subtract off f of x, which we see up here in black, is x squared plus 2x plus 3. Now make sure you get them parentheses though. And this will be all over h. Okay? Now it's just a matter of crunching that down. Here it goes. We get x squared plus 2xh plus h squared plus 2x plus 2h plus 3 minus x squared minus 2x minus 3 all over h. And you see a lot of this cancels. We can cancel out the x squared and the negative x squared, the 3 and the negative 3, the 2x and the negative 2x, leaving behind just 2xh plus h squared plus 2h all over h. And notice how you can factor in h out of the top. 2x plus h plus 2 all over h. And so we end up with this fully reduced as 2x plus h plus 2. And that's our difference quotient. This will give a formula for the slope of the secant line between any 2 points, as long as we give the x-coordinate of the left point, and we give the gap between the 2 points as h. Okay? Flange out.